In this problem, we have a simple spring mass damper system that we are going to apply two impulses to, a 20 Newton-second impulse, then we're going to wait a little bit and apply a second 10 Newton-second impulse. And we're trying to find the response of the system due to these two impulses. And we're going to do this two different ways. We're going to do it with a 0.3 second delay between the impulses, and then with a shorter 0.15 second, half as long as the first time delay. So we want to find that x of t response. So once again, in this example, we are given a lot of information that the modeling step is going to be quite easy. That we have our x of t response. We're given the k and the c and the m to use, and we're applying some forcing on our system. So in our model, the m equivalent, k equivalent, c equivalent are all just provided. So 5 kilograms, c is 10 Newton seconds per meter, and our k is 2,000 newtons per meter. So it's this forcing that we just have to do a little bit of work with so that we can express it in a way that we're going to be able to get our closed form solution. Now in this case, we have two impulses that make up our f of t. So an impulse falls under the type of forcing that we can, discrete forcing that we can put into our aggregate solution. So if we make our f of t a piecewise function, we're going to be able to get a piecewise x of t out in the end. So the way we can do this is we can include both of these impulses here, the initial one, which happens right away, and then the second one that happens at 0.15 seconds. Now, because these are only impulses, we could actually string them together because we're going to use the Dirac delta, but I want to write it still in this piecewise form so that we can use the piecewise solution. So our first interval is 0 to, we'll do it the first way, 0.3 seconds, and then at 0.3 seconds and onward. And actually, just for the sake of aesthetics, I'll make it exactly 0.3 seconds because that's where that second impulse occurs. So with our aggregate, we're going to have our F1 is going to be the first forcing. Well, that's that initial impulse of 20 Newton seconds. So that's how we can express it, 20 times Dirac delta of t. And over here, I'll have a picture of what's happening. So we have our t. So at 0, which I'll offset a little bit just so we can see what's happening. And then in the first case, 0.3 seconds, 0.15, 0.45, f of t. All right, so the forcing looks something like this. At 0 seconds, we have this impulse, this instantaneous force, a change in momentum, and then no forcing is going to happen. And at 0.3, we're going to have another impulse. So an impulse is this instantaneous, infinitesimally short duration force that instantly changes our momentum. Now we can't, to better represent it, what we can do is say it does have a very, very, very thin width to it. And what we say is that the area under this is going to be the actual impulse. So the thinner it is, the taller the actual force is if we were expressing it in terms of newtons of force rather than here what the impulse is. The impulse is the area under it. So this has an area of 20 Newton seconds under it, and the second one an area of 10 Newton seconds. And this is important because if we wanted to solve this numerically, we probably can't give it, if we're using something like an ODE45, we can't give it this instantaneous, really, really high force because it's probably not going to be able to detect it in the numerical solution. So what we might have to do is spread out the force over a longer period of time, but we have to ensure that the area under it is 20 Newton seconds for the first one and 10 Newton seconds for the second. So that's more for the numerical solution. We're not going to look at that in this case. We're going to put together our analytic solution. So for the second impulse, we still copy everything from the line above like we do for our aggregate solution. And I'll move this over a little bit here. Give ourselves some room. And then we're going to add that second 10 Dirac delta of t minus 0.3 in the first case. So the way the Dirac delta functions is it's going to be 0 anytime the argument inside of it is not 0. So for example, for the 20 Dirac delta t, 20 delta t, that delta t is 0 except for that moment that t is equal to 0. And in the second line, that delta of t minus 0.3 is 0 everywhere except when t is 0.3, because then the argument inside it evaluates to 0. So that's when it's going to shoot up there. So it's just this instantaneous function. And then again, kind of graphically, it's going to look like what we have down here. So this is a way piecewise we can express that f of t as these two impulses. And then we're going to change the interval and then that second delta in when we reevaluate this, striking it after only 0.15 seconds. So we have enough information to put together the equation of motion since we were given a lot of the relevant modeling information right away. Simple spring mass damper, it'll be in the form of mx double dot plus cx dot plus kx equals our right-hand side, f of t, which is expressed above. I won't rewrite it down here, but it's that piecewise function. And then we can put in our values, 5x double dot, 10x dot, 2000x equals f of t. And our identify, based on the left-hand side, 1 degree of freedom, just x, linear, damped, and we'll see what kind of damping we have. And we have general forcing on the right-hand side, right? In that it is not a simple harmonic motion. It's not just a sine or a cosine, so we need a little bit different approach. And in this case, we're going to use that aggregate approach because we were able to express the forcing as that piecewise function made up of just simple types of forces. In this case, two impulses, but we talked about ramps, impulses, and step functions that will allow us to do the aggregate solution. So our solution for x of t is going to be in the form of, here we'll have some x1 of t on that first interval, which the first time is going to be until 0.3 seconds. And then on 0.3 seconds and higher, we are going to have our x1 of t plus our x2 of t minus 0.3. And again, notice that the piecewise solution for x of t is going to look a lot like our f of t, where we have our f1 and we have our f2. So the solution for x1 comes from f1, the solution for x2 comes from f2. And in this case, the x1 and the x2 are both solutions for an impulse happening. So I can also put some detail down there. So the general solution from an impulse is that it's going to be the force of that impulse times e to the negative zeta omega n t over m times omega d times the sine of omega d times t. And for our x2, that's in the form of the amplitude of its impulse times, and actually the rest of it is exactly the same, sine omega d times t. So let's look at the parameters so we can find our x1 and x2, and then we're going to be able to form our entire solution from there. So parameters we're going to need, well, certainly we're going to need the natural frequency, root k over m. And again, the system we were provided both of those values. We have 2000 is our k and our m is 5. So the natural frequency comes out to 20 radians per second. And our zeta, we get c over 2m omega n. And based on the given values, we were told that c was 10. We're all in base units here. 2, 5, and the 20 we just found. So our zeta is 1 over 20. So we are underdamped. And our solution for x1 and x2 does presume that we have an underdamped system. So I'll just put a note up here and identify. We did confirm that we were underdamped, so our form of our solution is going to be okay to use. And we're going to need our damped frequency, as we see x1 and x2 require that, which is our omega n times 1 minus zeta squared when we have this underdamped system. Comes out to 19.97 radians per second, very close to, but not exactly, the natural frequency. And as far as the parameters go, this one's actually pretty simple. Those are all the parameters we're going to need to assemble our complete solution. Our initial conditions, we're starting at equilibrium. So our x0 and x0 dot are both 0 in this case. We're not told anything about an initial condition. So going to assemble this, we have, again, pretty straightforward. We've already written most of it. x1 of t, when we are from 0 to, in the first case, 0.3 seconds, and we'll change this for the second time. And at 0.3 seconds, we'll have x1 of t plus x2 of t minus 0.3, kind of just rewriting what we already have. But now I'll fill in the details for what x1 and x2 are. x1, that first impulse is 20 Newton seconds. And we're going to multiply that by, I'll rewrite some of the details here, negative zeta omega n times t over m times omega d times sine omega d times t. And we can simplify it now down a little bit. Omega d is, I'll cheat a little bit here, it's not quite 20, but I'll call it 20 so I can cancel out the 20 out in front. When we go into MATLAB, I'll be a little bit more precise with it. Our zeta and our is 1 over 20. Our omega n is 20, so that's going to go to 1. So this is going to be, that 20 cancels with that. We are going to have e to the negative t over 5 times sine of 19.97 t. As our solution for x1 of t. Yeah, it's going to be a little bit different because the the damped frequency was not quite 20, but this is good enough for the moment. x2 of t, like we said above, the only thing that's different on x2 is going to be the amplitude of the impulse. So we are told that it is only 10 for the second hit, and it was 20 for the first hit. So instead of rewriting this whole thing, it's going to turn out that this is just half of x1 of t. Because the f2 is half of the f1. So we don't have to rewrite the whole thing, it's just going to be that simple. Now we can plot our solution and see visually what this is going to look like when we hit our spring mass damper system with the hammer, wait, and then hit it a second time with, again, a little bit less of an impulse. Moving over to the MATLAB, I can put in all of those given system parameters here. So notice I'm going to make the time delay, that t1 equal to 0.3. That way I can easily change it for that second scenario where I have only a 0.15 second delay, and we'll see where that goes into play. I have here, I'm calling it actually J1 and J2 for those impulses of 20 Newton seconds and then the 10, and then those system parameters, 5 kilograms, 2,000 newtons per meter, and 10 Newton seconds per meter. So I can put some of these values in and see what I get. All right, so just to verify, natural frequency 20, 0.05 or 1 over 20 for zeta, the damping ratio, and the damped frequency 19.98 about with rounding. All right, now I'll define those response functions. And these are coming right from that definition. When we have an impulse, what the response is going to look like. So the x1 I'm putting in and the x2. So notice here, this will be an exact calculation where I'm not going to make that, that small consideration. I will get that J1 and omega d will not quite cancel. So the MATLAB will give us a little bit more precision. And the x2 I am defining here using the J2. All right, so this is a direct definition with the amplitude of those impulses present. And I'll simulate this over 3 seconds to see what happens here. In 262 is where I assemble my piecewise solution. So the first one triggers at 0 seconds, that's my x1 of t. And then my second response is going to trigger at t1, which for the first case is 0.3 seconds. So notice here I have my x2 of t minus 0.3, and then the piecewise part, it's going to turn on as soon as my timer is above 0.3 seconds. So like we saw before with assembling our piecewise, that's how x of t can be put together here. So in my plotting, I'm actually going to take a look at 2 different things. I'm going to plot in black here that total response when I hit the system with the hammer 2 times. And I'm also at the same time going to plot just x1 of t. So what if I only hit it the first time and didn't hit it a second time, just for comparison in this problem. So both of those we're going to see. So let's run this and see what the response looks like. And this blue line indicates when that second hammer strike takes place. All right, so once again, black is the total response when I hit it with the hammer twice, and red dash is if I only hit it with that first one. So until that second hammer strike, well, they are exactly the same because the first system nor the second system knows the second strike would be coming until that 0.3 seconds. So they are identical to each other, and they should be. Now, again, on this blue line, the 0.3 seconds, that's where I hit it that second time. And we see what happens is that our system with that double strike has a much higher amplitude. It goes all the way up to about, let's say, 0.23, 0.225, somewhere in there. So the amplitude is going to be higher after that second strike than if I had not struck it that second time. But given enough time, and we are only looking over 3 seconds here, the ringing, the oscillations are going to die out as time goes forward because I do have damping in that system. However, the amplitude of that system where I struck it the second time is higher in all places now versus the system where I only struck it the first time. And let's notice on this one, when I struck it at that 0.3 seconds, the systems, both of them were the same up until this very moment, had a positive velocity. If we notice, the slope of this is positive, meaning that they were both traveling in the downward positive x direction. Again, that was their direction of travel. They are above that equilibrium point because their x value itself is negative. However, their velocity is positive. They're traveling downward. So the system was struck in the downward direction as it was traveling in the downward direction, and we see that that increased what the response was, what the amplitude of that response was in the system where we account for that second hammer strike, where we get that larger amplitude. But let's compare to a system where we strike it sooner. And this is that second part of the original question. What happens if instead of waiting 0.3 seconds, we only waited 0.15 seconds? Everything else in our system is going to remain the same. Some things will be automatically recalculated by the virtue of using MATLAB. The responses are going to look the same in general, but when we assemble it, now that T1 is the 0.15, but all of that will be automatically taken care of using the code. So let's see what happens when we wait a shorter amount of time for that second hammer strike. And we see here the responses. Again, black is with the second strike, red is without. In this scenario, the effect is the opposite. If we look at the amplitude of the system with the second impact, its amplitude gets less compared to the system where we only impacted it the first time. So let's see why that's happening. Again, all we changed is striking it sooner. So now the blue line is on the 0.15 seconds, and we see that in the systems, as they're going along, now their velocity is negative. They're traveling in the upward direction when that hammer strike in the downward direction comes. So it's traveling the opposite direction of the hammer this time, and that's going to attenuate, it's going to lessen the amplitude after that hammer strike. So by simply changing the timing of that second strike, we have impacted in the opposite direction the effect on the amplitude in this system. And what we can think of is compare this to on a trampoline, a large trampoline, if we have a double bounce, where depending on where we are landing on the trampoline when we are struck with that double bounce, either we can go up much higher, maybe twice as high if someone double bounces us, versus if the double bounce occurs too early and we hit the trampoline as we're going down, the trampoline is coming up, that's going to lessen the amount of rebound that we experience on the trampoline. So in summary here, we were able to assemble our total solution based on the piecewise forcing that we created. These two impulses, F1 and F2, provided us with our solutions x1 and x2, which we put together with our piecewise response. And the first time we went through this, we delayed the hammer by 0.3 seconds before the second strike, and then reevaluated it by waiting less amount of time, the 0.15 here, changing some of these offsets. We found our parameters and got our full solution and then plotted it in MATLAB.